So now let's talk a little bit about what a permutation is. So it's worth thinking about what permutations are counting. When we talk about permutations, we care about who is sitting in which chair. So for example, here we have Clarissa sitting in the first chair, we have Herb sitting in the second chair, and we have Leslie sitting in the third chair. However, a different combination would be Herb sitting in the first chair, Clarissa sitting in the second chair, and Leslie sitting in the third chair. These two distinct combinations would be counted as two different permutations. These are the same three people, however, we are putting them in a different order. Okay, here the order matters. So there is a total of 6 different permutations involving Clarissa, Herb, and Leslie. Basically, there's 6 different ways in which we can rearrange these 3 people in 3 chairs. So if we move on to the next slide, these are the 6 possible permutations. Here, Clarissa, Herb, Leslie, Herb, Clarissa, Leslie, and you can check these out. Now in the permutation world, we would count all of these as 6 different permutations. These are 6 different ways in which we can sit these people, because the order matters here. Having Clarissa sit first is definitely different than having Clarissa sit last. But now, what if all we cared about was the 3 people we were choosing, but we don't care, or we didn't care in what order they are sitting or in which chair they are sitting? The 6 permutations below represent the same people, hence all 6 permutations would make the same combination. So again, just to reiterate, let's say we don't care what order they are sitting in. Let's just say we want 3 people and we want them to sit in 3 chairs, and those 3 people happen to be Herb, Leslie, and Clarissa. All of these distinct permutations would become the same combination. Alright? And that's the idea of today. We're going to be talking about combinations, and in combinations, the order doesn't matter. We don't care about who's sitting first, who's sitting second, who's sitting third. All we care about is the items, or in this scenario, the people. So let's go ahead and talk about combinations from an algebraic standpoint, and then we'll apply them to some examples. So here is the algebraic notation. We have n, and then we have a k below it, and we have a set of parentheses. This is read as n choose k. And now to compute this, here is what we do. In order to calculate n choose k, we're going to calculate the number of permutations, and then we're going to divide by k factorial. So let me just show you a quick demonstration of why this is true. And again, this is just a demonstration. It's not a rigorous proof or anything, but here that we had 3 people and we had 3 chairs. Because we have 3 people here, we have a total of 3 factorial rearrangements of these 3 people. And that 3 factorial is equal to these 6 distinct permutations. But now remember that here we calculated the number of permutations, and each permutation is saying that this possibility is different from this one, and so on and so on. So to eliminate all of these repeats or repetitions, what we have to do here is divide by 3 factorial as well. So here we have 6 over 3 factorial, but that's 6 over 6, and we have 1 possible combination. So basically dividing by that k factorial helps us eliminate all possible repeats. Because remember, if we don't care about the order, this combination should be the same as this one. So here, that's how we calculate combinations. And we can even take this a little bit a little bit further. The number of permutations, we know how to calculate that as well. And well, let's actually just do it. So here we have n choose k, and that's equal to n factorial over n minus k factorial. And remember, this is all being divided by that k factorial on the bottom. Okay, but now we know how to multiply, or we know how to divide ratios, right? We can do that keep, switch, flip thing. So we're going to keep the numerator, our numerator being n factorial over n minus k factorial. We're going to switch the operation. So instead of division, we're going to get a multiplication. And then instead of, for the final part, we're going to flip the denominator. So now we're going to multiply it by 1 over k factorial. And then we can multiply across. So n factorial times 1 is just going to be n factorial. And on the bottom, n minus k factorial multiplied by k factorial. I can commute these and write it as such: k factorial times n minus k factorial. And this is what you typically see on the textbook. The combination formula n choose k is equal to n factorial divided by k factorial multiplied by n minus k factorial, with again this k factorial being the quantity that's going to eliminate all the possible repetitions, or all possible repetitions. So just to point out again and to reiterate this here, order does not matter. And we'll talk more about this soon. But for now, let's focus our attention on being able to compute such quantities here. So let's begin with the first example. So focus on the formula, and let's try example 1. Compute 6 choose 3.